the end behavior, x approaches negative infinity, the function approaches, because it's negative, it's opening downwards, so it's going to negative infinity. As x approaches positive infinity, the function approaches positive infinity. We know that we have x-intercepts at 1 and at 5. We have an axis of symmetry halfway between that. We calculated that to be 3. So you want to label your graph x equals 3. We found our vertex to be at 3, 8. Now we can find the other point, so we make your graph go through it nicely. A couple different ways. We could plug the number 2 in, because when x is 2, we're looking for where the dot is when x is 2. We could test that theory. So we get 6. The other way to do it, you know that the parent function is typically 1 over and 1 down for the negative x squared. But here we're doing a stretch of 2, so it's going to be 2 more down. So we still get the same location, either way you think about it. So y equals negative 2, x minus 1, x minus 5. Here we're looking at intercept form. Our intercepts are going to be negative 3, comma negative 5. Our vertex is going to be x equals p plus q divided by 2, which is negative 3 plus a negative 5, which is negative 8, which is at negative 4. Divide that negative 8 in half. So we get an answer here to be negative 2. So our vertex looks to be at negative 4, negative 2. So on our graph, we have our, well, funny notation here, huh? This is not the right notation, sorry. Usually find my mistakes eventually. So your negative 3, comma 0, and your negative 5, comma 0. It's not a point, negative 3, negative 5. They're two separate points. So at negative 3, 0, and negative 5, 0, we have an axis of symmetry at negative 4, which is halfway between it, and we label that. We calculated our vertex to be at negative 2. Now we're going to look at some other points so we can draw our graph well up throughout our grid. We can look out here at x equals negative 2, x equals negative 1. One way, the parent function would be over 1, up 1. Now we're going to go 2 more than that. So x is 2. Parent function is x is 4. We're going to go 2 times that. We should be up here. If you're not sure about that, you can plug in the number x equals negative 2 2 times negative 2 plus 3, negative 2 plus 5. See that that crosses at 6. So when x is negative 2, 1, 2, 3, 4, 5, 6. It's exactly where it lands. Then we reflect it over the axis of symmetry. And this graph is called y equals 2, x plus 3, x plus 5. So our axis of symmetry is the x value of the vertex. We know we have a minimum, and that's going to be the y value of the vertex. The domain is always all real numbers, and the range is y is greater than or equal to negative 2. We could also do that in interval notation. This guy's interval notation for all real numbers. And behavior, as we look to the left, the function is going up. As we look to x goes to infinity, the function is going upwards. We look to the right, the graph is going upwards. On the other side, we're going to look for the max and the min value of each function. We look here, a lot of people get confused by looking at this type, but this is vertex form. And in vertex form, we know that the vertex is given to us. And because the a value is less than 0, we know that this has a maximum point. And the maximum point is going to be the k value. In intercept form, we find out our vertex by using the p plus q divided by 2. So p is 1, the q is 4, so that gives us 5 halves. Then we got to plug that back in. So minus 1 would be 2 over 2. 5 halves minus 4 is 8 over 2. We want common denominator so we can calculate this together. So we get 3 halves and we get negative 3 halves. So 3 times 3 is 9, times 2 is 18. 2 times 2 is 4. That can be reduced to negative 9 halves. So we can see the vertex is 5 halves and negative 9 halves. Well, what this tells us is that the a value is greater than 0, so we have a minimum value, and y equals negative 9 halves is that minimum value. Okay, if we're at a golfing range, hitting off a raised platform, we have an equation of negative 0.5 t plus 2 t minus 5, where your height in feet as a function of time in seconds. This models your height in feet. So we got to find some different parts of it. We know that we're just looking at the first quadrant because this would be seconds, which is your time, and then your height, this should be your feet, which is your height. So at -2, that would be off our grid, but we don't care about time that's negative. We have time of 5 that it's taking the ball to hit the ground. So our intercept is at 5, 0. In terms of the graph, it's also -2, 0. To figure out the vertex, we're going to take the P, which is 5, and the Q you might call -2. So that's 3/2. So our Y is going to be -1/2 times 3/2 plus 4/2 times 3/2 minus 10/2. Because 10/2 is a value of 5, 4/2 is a value of 2, they have to have common denominators. So this is giving us positive 49, 7 and 7 is 49 times 1, 2 times 2 is 4 times 2 is 8. So what we're seeing this as, 6 times 8 is 48, so there's 1/8 left over. So when X is 1.5, we're going to be up at 6 and 1/8. So we have a vertex with an X value of 3/2, which is 1.5, and a Y value of 49/8. The axis of symmetry is X equals 3/2. We have a maximum number because it's opening downwards, which is our max, and a Y value of 49/8, which is 8 1/6. Your domain, well, is it the domain of the equation or is it the domain of the problem? A reasonable domain for this would be t values that are greater than or equal to 0, because we don't care about time prior to when you're about to hit it off. And the range, that's what we need to figure out. And what's going to happen at 0 seconds? So we need to plug a 0 into our problem. So at 0 plus 2 and 0 minus 5. That gives us -10 divided by 2 is 5. It'd be a positive 5 because of another negative. So at 0, we're up at 5. So our range is still that maximum value. So it's Y values are less than or equal to 49/8. But if we want to keep it into the real world, the golf ball can't go underneath the ground, so it's greater than or equal to 0. But this 5 allowed us to see the path of the ball. For the end behavior, the X value, it's not really approaching negative infinity, it's only approaching 0. X value can get closer and closer to 0 from the positive side. The Y value is approaching 5. As X approaches, the biggest it can approach is 5. The Y value is approaching 0. So a little bit different end behavior than we're used to, because this graph doesn't go on forever. It has a time that's limited, and it has a height that's limited. How high above the ground did the ball reach? A y value of 8 1/6 feet. What do the X-intercepts mean in the contents of this problem? It would be when the ball, where the ball touches the ground, or when the ball touches the ground. And how tall is our raised platform? Well, at 0 seconds, we are at a height of 5. So 5 feet. Okay, now we're going to write an equation using this intercept form. We're used to finding two numbers, and then the value in between is our vertex. But in this case, we have our pair of numbers and another pair of numbers and another pair of numbers with no value in between. What we do have, though, are the two zeros. These two zeros are considered your x-intercepts because it's y is 0. Y is 0 will give you your x-intercept. So this is your p value and this is your q value. So with those being our p's and q's, we have y equals a x minus p x minus q. That's the typical format. So a y, we can pick any y value we want. Let's go with this one. So y of 4 and x of 0. The p was negative 3. X is 0 and our q was 1. So we're going to get positive 3 times negative 1, so that's an a value divided of 4/3. Negative 4/3. So our equation is y equals negative 4/3 x plus 3, because it's minus a negative, x minus 1. Okay, now we're going to question this here a little bit. We do have a bit of a mistake. We have the 4s. We have our q value. We're going up by 1, 2, 3. But if you look in this direction, we're going negative 1, negative 3, 4. That's not the way that this can work. These have to all go by a scale of 1. So if that's going by a scale of 1, this has to be going by a scale of 1. So our p value should actually be, because it's our intercept, it has to be negative 2. So our p value has to be negative 2. Which is going to give us a positive 2, which is going to give us a negative 2 for an a value. And a negative 2 for an a value. So we're going to look here, and we're going to try to type that into our graphing calculator. Negative 2 for our equation, with x plus 3 and x minus 1 as our equation. We can see that real quick as a graph, and it's crossing where we're talking about. We're going to look at the table where x is 0. Looks like I'm getting 6 and I'm not getting 4. That's because in my equation I didn't switch this to a 2, right? Our p value we said was a 2. Gotta check your work. So there's our 0 of 4, and our 1 of 0, and our 2 of -8, and 3 of -20. Phew! That was a little tough to change the question. You won't have to worry about changing questions, but in the right notation, that's the way we would solve that. Okay, so our intercepts are going to be -2, comma 0, and 1, comma 0. The vertex, we haven't calculated the vertex. The vertex has an x value of p plus q divided by 2, which is -1/2. And the y value would then be -2 times 1/2, or 1/2 plus 2, and 1/2 minus 1, which gives us -2, 1/2, -1/2. So these two can cross off. We get -3, we get +3 halves. So we get -1/2 and +3 halves. We should be able to see that in our graph. Again, we have -1/2. That should be a -1/2, which would give us -3 halves, which we get 3 times 9 times 18. So this should be +18 over 4, which is 9 halves, which is a 4.5. Looking back at our table, if there's a neat way that we can go second trace or second calc. We can look for the maximum value. We can look to the left side. We can look to the right side, and we can check in the middle. And you'll see that that gives us that -1/2 and 4.5. We'll talk more about that process in the future, but you can see where that math came from and how quick a little mistake can start to change you up. So the axis of symmetry is x equals -1/2. We know we have a maximum point where the y of the vertex is, and it was at 9 halves was the vertex, not 3 halves. We calculated that right there. The domain is always all real numbers, and the range is y is less than or equal to 9 halves. The end behavior, as x approaches -infinity, the function approaches -infinity. As x approaches +infinity, the function approaches -infinity. It always approaches the same direction. Both will go down for a quadratic, or they'll both go up. Here's another method. The a value in the equation, it's not double, it's half the value of the second difference. So we come over here. This is a different way to find your a value. -8 minus 0 is -8. 0 minus 4 is -4. 4 minus 4 is 0. 4 minus 0 is 4. 0 minus 8 is 8. And 8 minus 20 is 12. Well, you notice that all of those differences are not the same. If they were the same, then this table would be linear. So next we're going to look at it. -8 minus 4 gives us a -4. -4 minus 0 gives us a -4. 0 minus 4 gives us a -4. 4 minus 8 gives us a -4. So you notice, seeing every time we do this, we get a negative 4. So we have the second difference is negative 4, and we got to take half of that. So half of negative 4 is the negative 2. If you don't like to plug in a number, if you don't like to do it this equation format, you can do the second difference to help you determine what the A value is. Your choice.